What is a Peltier cooler? Fridge, whatever you want to call it.
Peltier effect. It's thermoelectric effect.
Oh.
So where's a nice picture of this? There we go. So you put a hot side and a cold side across a transistor, which then drives the electrons from one side to the other. You get a current that pops out of it.
I see.
Or you could do it the other way. You could push a current into it, and then you'll separate a hot side from a cold side. So if you put your refrigerator on the cold side, you get a cold box. You get your hot side, you put it out to the outside world.
So this setup here is somehow pulling energy from the cool side to the hot side.
Yeah. So I guess you could view it from a conservation of energy way.
Okay.
You're converting the electrical potential from the high voltage to the low voltage, and then changing that somehow quantum mechanics into a thermal potential, hot side, cold side. You're separating them.
I guess I don't understand how this works. I hook it up. Okay, so I have this circuit with a.
So the device. Let's make this bigger. The device would be this the hot side, the cold side, and the PN junction in here.
Yeah.
I guess they're not junction; they're separated. Okay. And then the supplied power is the outside stuff.
Okay. And
so I push current this way, or maybe electrons this way, however you want to think about it.
Yeah.
And then through the quantum mechanics. Oh man, it's been a long time since.
Okay. So on the turquoise or the turquoise, whatever that is, the electrons there are being pulled down.
Opposite of the current. Yeah.
Okay. And the holes on the right side, which are the positive vacancies, are getting pulled down as well.
Yep. Same direction as the current. I like that.
Okay. So I see that's happening because we've hooked it up to a voltage, and so the holes and the electrons act in a specific way. How is that creating heat flow from one side to the other?
So let's read the description. A thermoelectric circuit composed of metals of different Seebeck coefficients, p-doped and m-doped semiconductors, configured as a thermoelectric generator. If the load resistor at the bottom is replaced with a voltmeter, the circuit then functions as a temperature sensing thermocouple. Oh yeah, that's true. So I guess Seebeck coefficient is the next thing to chase. Seebeck effect. German physicist Thomas Seebeck discovered that when two wires made from dissimilar metals are joined at two ends to form a loop, if the two junctions are maintained at different temperatures, a voltage develops in the circuit. Oh, that's the result, but not necessarily the explanation.
Okay. Actually, we can go back to that thermoelectric, that picture. So they're saying, the original one. This is very similar, but yeah. So they're saying, if we read the description, it says that at the bottom, if the load resistor at the bottom is replaced with a voltmeter, then the circuit functions as a thermocouple. So the load resistor is the holes in the electrons are coming back and recombining, which then releases energy.
So the way that I described it, this would have been a current source or supplied voltage, and then you push the current around.
Okay.
If we were to instead replace this with a variable voltage or variable volt reader, so I guess a voltmeter, then this thing will naturally, variable voltmeter, which means there is some type of circuit, which means this thing will naturally push electrons around.
Okay.
So am I going with the right way with this? So if this is a voltmeter, depending on this temperature differential, you'll get a different voltage that comes out.
I see. So, okay. So you have a hot side and a cool side. The holes on the right side, the yellow, go down. That's positive. And the electrons on the left side go down, so the electrons accumulate on the left side and the holes accumulate on the right side. That creates a voltage difference that we can now measure. So that's a thermocouple.
Right. Although I think what I said was wrong, but I think what you said was right.
Right. But if we put a resistor there, then the holes and the electrons are free. The charge is freely allowed to flow through the circuit. So somehow the holes and the electrons recombine somewhere. When holes in where's the, I guess, how is the energy getting transferred at all? I don't see how the energy.
Where's the power coming from?
Where's the heat flow? It goes from where to where, and how's it carried? I don't get it. Oh no.
So I think it's the Seebeck coefficient.
Okay.
It's something to do with the electron orbitals being filled at room temperature.
Mm-hmm.
So if you have metal A that at room temperature has a bunch of electrons that are available to run around, so conduction band. But then if you have metal B, which has a bunch of vacancies available, then if you bring them together, the electrons will flow from the material that has available electrons to the lower one.
Yeah.
But then if you raise their temperatures, then you can change the distribution, which now puts them at different voltages, I think.
Okay. I like this. And when an electron and a hole recombine, that gives off energy. Is that right?
Yeah. Or I guess if an electron falls into a hole, then it's now reduced its electric potential.
Which means it gives
use that energy somewhere else.
Okay. So if you create a hole and an electron, then it requires energy to do that.
Sure.
And when they're recombined, or an electron falls into a hole, then that gives off energy.
Sure.
So if we're creating electron hole pairs at the hot side, that's pulling energy out of the hot side and creating the electron hole pair. If we recombine them at the cool side, then that gives off energy and warms the cool side. So pull energy from the hot side and give it to the cool side. Is that what we want?
I think so.
But that's we want the opposite direction, right? Because heat spontaneously goes from hot to cold. So we want to go from cool to hot, right?
So then when you generate a hole, you make a hot and a cold. Oh my gosh, I just mushed the ideas together.
Is there another thing written on Wikipedia about how it works in the...
Gosh, thermoelectric effect is the right one.
What about the Peltier... What's it called?
Peltier-Seebeck effect. The separation derives independent discoveries by French physicist Jean-Charles Athanas Peltier and Baltic German physicist Thomas Johann Seebeck.
Okay.
Joule heating, the heat that is generated whenever the current is passed through a conductive material, is not generally termed thermoelectric effect. Yeah, that's correct. Okay. Oh, interesting. The Peltier-Seebeck and Thomas Thomson effects are thermodynamically reversible, whereas Joule heating is not.
Okay.
So if I push a current in one way, from right to left, I can generate a hot to cold and the up to down. But if I push the current from left to right, I would flip that, make it hot on the bottom, cold on the top. So reversible.
Okay.
Or I guess no, that's not reversible. Reversible meaning if I push the current from right to left, I generate a hot top on the bottom. Okay. Or I can make the hot the top on the bottom and then generate the current.
Okay.
Like the order doesn't matter.
Okay.
I need a